Earth, my good sir, you are a madman genius, and so is this cowboy over here, Jump Science. Of course, these are limited features in differentials that I want you to take a look at, because this right here will probably be my first diagram within the physics set. Let's just cut that over here. Do that. We're going to say, what is physics, physical analytics, and vocabulary?
Hey everyone, Path here, and welcome back to Relativity relatively quickly. In this episode, we'll look at some of the basic equations used in Galilean relativity, and then we'll set the scene for Einstein's special relativity to come into the picture. If you want to find out what relativity is in the first place, as well as some of the basic principles of Galilean relativity, then check out the previous episode of this series up here. Though that shouldn't be necessary in order to follow along with this video. As always, if you enjoy this video, then please hit the thumbs up button and subscribe for more fun physics content. Let's get into it. Let's start by recalling that two observers that are moving relative to each other, let's say in the x direction, with a relative speed v, will have different observations about an object that is potentially stationary in the first observer's reference frame. What we mean by this is that the first observer sees this object as being stationary, as well as the second observer moving past them. Plotted on a graph of position and time, the object's position doesn't change in this first unprimed reference frame. But the second observer, with what we call the primed reference frame, is moving relative to the first observer in the x direction.
Relative to
so
the
from
first
their
observation of their height
the object
and weight,
and the first observer actually move,
because that's going to change. 40 centimeters and
now,
150.
diagrammatically, what we've seen so far
that
is
being
a really
primed,
nice
now
way
if
to
that
display the
observer
motion
is
of
in there,
the same
they should both
object
make that same
in different
projectile
reference
semi-imperial
frames,
mass.
the unprimed reference frame and the primed reference frame. But this motion was a relatively simple one, stationary in one frame and moving at a constant speed in the other frame. And even then, we had to work out at each point in time what its position would be in the primed reference frame if we just knew its position in the unprimed reference frame. What we really want is a set of mathematical equations that will take us from one perspective to the other very easily. Basically, if we know the value of x at any point in time in the unprimed reference frame, then we can imagine that the value of the coordinate in the primed reference frame, which is x prime, must depend on the value of x as well as the relative speed between these frames and how long it's been since the frames crossed over. Because the longer it's been, the further their origins are from each other, and so the bigger the difference there's going to be between x and x prime. So between what is measured by the first observer
and so whichever
and what
way
is
you
measured
want
by
it
the
to
second
go
observer in
is
terms of
where
the
that science
position.
is, because it probably wouldn't be a stick person,
but
if there was a standard model stick person for jumps,
x prime is equal to x
when
minus
it's useful
vt.
to
We can
think
see
about
that at t is
rotational
equal to
force
0,
being
the frames are at the same
weighted
position, they have the
object,
same origin. So the two frames say that the position of the object has the same coordinate value. Then 1 second later, the frames are this far apart. So the primed reference frame says the position of the object is this, and then another second later, it's this, and so on and so forth. Now remember, the way that we are showing these diagrams makes it look like the primed reference frame is just wrong or silly, because its coordinates are moving, so of course it would make an incorrect measurement of the position of the object.
I can't get under the
But if we
timeline.
switch to the primed reference frame, then we can see that from its perspective, it's actually the object and the other reference frame that are moving. And even from the perspective of the primed reference frame, we can see that because the unprimed reference frame and the object are moving away from us at the same speed, that anybody in the unprimed reference frame will measure a constant position for the object. In other words, even from this perspective, we can see that another observer in the unprimed reference frame would think that the object is not moving, it's stationary. Now, interestingly, in doing whatever we've done so far, we've made a very deep assumption that isn't immediately obvious. We've assumed that both reference frames always agree on
can generalize
time
that,
values.
and you could say,
Like,
well, off
even
of
though they
those
disagree
generalized
on the
points,
position coordinate,
I could
they
then
both
say
seem to agree
they're close
on
to
when
that,
1 second
the
has
things that I would
passed
need, the things
after
that
the
have to
crossing
have
of the
happen in
axes,
that
for
situation.
example,
That's physics.
and they seem to agree on when
Right,
2
before we
seconds
get
have
into
passed,
programming
and so
it,
on. More generally, this signifies that we've assumed the existence of some universal time.
To those limits,
all reference frames in Galilean relativity assume that everyone in every reference frame agrees on the passage of time, how long 1 second is. And this seems like common sense, but it isn't actually very true. When we start looking at special relativity and general relativity, we'll see that these equations here that transform from one frame's perspective to another look quite different, and that time passes at different rates for different observers moving relative to each other. More on this in a future episode. For now though, I'm going to finish up here with a short video discussing Galilean relativity and the equations that transform from one reference frame to another. If you enjoyed this video, then please hit the thumbs up button and subscribe for more fun physics content. Let me know if there's any parts of relativity, whether that's Galilean, special, or general, that you'd like me to cover in this series. And also if you enjoy this short format series with multiple videos discussing essentially the same topic. Please also do check